So in this video we'll solve the sums of class 12th physics magnetic material. Let's look at the first sum. When a plate of magnetic material of size 10 centimeter into 5 into 0.2 centimeter, that is the length, breadth and thickness, is located in magnetizing field of 0.5 into 10 raised to 4 ampere per meter, then a magnetic moment of 5 ampere meter square is induced. Find out the magnetic induction in the rod. So solution, let's find out first of all the volume of this magnetic material. So volume will be 10 into 0.5 into 0.2, which will be equal to 1 centimeter cube. Now we know 1 centimeter cube is 10 raised to minus 6 meter cube. So the volume will come out to be 10 raised to minus 6 meter cube. And the magnetizing field is given to us as H equal to 0.5 into 10 raised to 4 ampere per meter. Also the magnetic moment is given to us as small m 5 ampere meter square. We need to calculate the value of B. So let's first of all calculate the magnetization M. Magnetization is given to us as magnetic moment per unit volume, which is 5 divided by 10 raised to minus 6, which comes out to be 5 into 10 raised to 6 ampere per meter. The magnetic field B is equal to mu naught H plus M, which is equal to 4 pi into 10 raised to minus 7. H is 0.5 into 10 raised to 4 plus m, that is 5 into 10 raised to 6. Now to add this we have to make the power equal, so I can write this 4 pi into 10 raised to minus 7 into 0.005 into 10 raised to 6 plus 5 into 10 raised to 6. Now I can add them, which will come out to be 4 pi into 10 raised to minus 7 into 5.005 into 10 raised to 6, and multiplying this all we will get magnetic field B equal to 6.29 Tesla. Let's look at the next one. A rod of magnetic material of cross section 0.25 centimeter square is located in 4000 ampere per meter magnetizing field. Magnetic flux passing through the rod is 25 into 10 raised to minus 6 Weber. We need to find out relative permeability mu r, magnetic susceptibility chi, and magnetization m. So first of all, solution, area is given to us as 0.25 centimeter square, which is 25 into 10 raised to minus 6 meter square, and magnetizing field H is given to us as 4000 ampere per meter with the magnetic flux as 25 into 10 raised to minus 6 Weber. We know B is equal to flux upon area, which is equal to 25 into 10 raised to minus 6 divided by 25 into 10 raised to minus 6, which comes out to be 1 Tesla. So the magnetic field is 1 Tesla. Now in order to calculate relative permeability, we know B is equal to mu H, that is permeability of medium. Now mu is equal to mu naught into relative permeability. So B is equal to mu naught mu R into H, which implies mu R will be B upon mu naught H. So 1 upon mu naught is 4 pi into 10 raised to minus 7 into H is 4000. So calculating this we get mu R equal to 199. Now since this is a ratio of permeability divided by absolute permeability, so this is dimensionless. So next thing is magnetic susceptibility. So we know one formula, that mu r is equal to 1 plus chi, that is the magnetic susceptibility. So which implies chi will be equal to mu r minus 1, that is 199 minus 1, which is equal to 198. So this is the magnetic susceptibility. Third thing we need to calculate is magnetization of the rod. So the magnetization M is given to us as susceptibility into magnetizing field, which is equal to 198 into 4000, which comes out to be 7.92 into 10 raised to 5 ampere per meter. So let's look at the next one. The work done for rotating a magnet with magnetic dipole moment m through 90 degree from its magnetic meridian is n times the work done to rotate it from 60 degree. So find the value of n. So solution, we know that in a magnetic field, if you place a bar magnet, it will always points towards the magnetic field. Now in order to rotate it through an angle of 90 degree, we need to do work, and that work is given to us as W equal to mb cos theta 1 minus cos theta 2. Theta 1 is the initial angle and theta 2 is the final angle. So in the first case we need to rotate it by 90 degrees. So W1 will be mb cos theta 1. Now since the bar magnet was already along the magnetic field, the theta 1 will be 0. So cos 0 minus cos, we have to rotate it by 90 degrees. So cos 90, which will be 0. So W1 comes out to be mb, since cos 0 is 1. In the next case, we need to calculate the work done to rotate it through 60 degrees. So W2 will be mb cos 0 minus cos 60, which is equal to mb 1 minus cos 60 is half, which comes out to be 1 by 2 mb. Now they have given us that the work done to rotate it by 90 degrees n times the work done to rotate it by 60 degrees. So W1 is equal to n times W2. So W1 is given to us as, we found W1 to be mb, and n times W2 is half mb. So mb get cancel and n will be equal to 2. So this is the value of n. Let's look at the next one. An electron in an atom is revolving around the nucleus in circular orbit of radius 5.3 into 10 raised to minus 11 meter with a speed of 2 into 10 raised to 6 per. Find the resultant orbital magnetic moment and angular momentum of electron. So solution, we know the orbital magnetic moment is given to us as half EVR. So let's put all the value. Half into charge of electron is 1.6 into 10 raised to minus 19 into the velocity is 2 into 10 raised to 6 meter per second, and the radius is given to us as 5.3 into 10 raised to minus 11. So calculating this, we get orbital magnetic moment to be 8.48 into 10 raised to minus 24 ampere meter square. Next thing we need to find out is the angular momentum. So angular momentum L is given to us as mvr. So mass of electron is 9.1 into 10 raised to minus 31 kg into velocity is 2 into 10 raised to 6 into the radius of the electron is 5.3 into 10 raised to minus 11. So calculating this, we get angular momentum to be 9.65 into 10 raised to minus 35 kg meter square per second. So let's look at the next one. A paramagnetic gas has 2 into 10 raised to 26 atom per meter with atomic magnetic dipole moment m equal to 1.5 into 10 raised to minus 23 ampere meter square. The gas is at 27 degrees Celsius, and we need to calculate the maximum magnetization intensity of this sample. So solution, magnetization is given to us as magnetic moment per unit volume. Now since there are n number of molecules, this will be n times mv. Here what they have given us is number of molecules per unit volume, that is 2 into 10 raised to 26. So n by v will be 2 into 10 raised to 26, and small m is the magnetic dipole moment, that is 1.5 into 10 raised to minus 23. So putting this value, you will have 2 into 10 raised to 26 into 1.5 into 10 raised to minus 23. So the magnetization will be 4.5 into 10 raised to 3 ampere per meter. So this is the maximum magnetization for all the molecules. Now in second case, what they have asked us is that if the gas in this problem is kept in a uniform magnetic field of 3 Tesla, is it possible to achieve the saturation magnetization? So the condition for saturation magnetization is that mb should be greater or equal to 3 by 2 kV. Now if you don't know what are these terms, so mb is the maximum energy provided by the magnetic field, and 3 by 2 kVt is the thermal energy, or you can say average thermal energy of this atoms. Let's calculate mb and let's calculate 3 by 2 kVt, and let's see whether this condition is satisfied or not. So MB will be 1.5 into 10 raised to minus 23 into magnetic field, that is 3 Tesla, which comes out to be 4.5 into 10 raised to minus 23 joules, since this is energy. Now 3 by 2 kVT will be, the temperature is 27 degrees, so T is 27 degrees, which comes out to be 300 degree Kelvin. So 3 by 2 into K is 1.38 into 10 raised to minus 23 into T is 300 degree Kelvin. So solving this, we'll get 6.21 into 10 raised to minus 21 joules. Now since this is greater than this energy, this condition is not satisfied, and we can say that it is not possible to achieve saturation magnetization. So I hope you understood this sum. Let's look at the next sum. A magnetic needle placed in a uniform magnetic field has magnetic moment 2 into 10 raised to minus 2 ampere meter square and moment of inertia 7.2 into 10 raised to minus 7 kg meter square. It performs 10 oscillations in 6 seconds. What is the magnitude of magnetic field? So solution, we have been given small m, that is magnetic moment 2 into 10 raised to minus 2 ampere meter square, and moment of inertia to be 7.2 into 10 raised to minus 7 kg meter square. Now we know time period is the time required for one oscillation. So they have said us that for 10 oscillations we require 6 seconds, but we require time for one oscillation, that is the time period. So for one oscillations, how many seconds will be required? So x will come out to be 6 by 10. So this is our time period for one oscillation. So your time period will be equal to 6 by 10, that is 0.6. Now we know the formula, T equal to 2 pi root under I upon mb. Since we have to calculate the magnetic field, we'll just square this, so we'll have T square equal to 4 pi square I upon mb, which implies B will be equal to 4 pi square I upon mt square. So let's put all the value. We'll have 4 into 3.14 square into moment of inertia, that is 7.2 into 10 raised to minus 7 divided by magnetic moment 2 into 10 raised to minus 2 into t square, that is 0.6 square. Now solving this, you will get magnetic field to be 39.48 into 10 raised to minus 4 Tesla. Let's look at the next one. A short bar magnet is placed in an external magnetic field of 700 Gauss. When its axis makes an angle of 30 degree with the external magnetic field, it experiences a torque of 0.014 Newton meter. Find the magnetic moment of the magnet and the work done in moving it from its most stable to most unstable position. So solution, first of all, the magnetic field B is given to us as 700 Gauss. Now 1 Gauss is equal to 10 raised to minus 4 Tesla. So this will be 700 into 10 raised to minus 4 Tesla, which will come out to be 0.07 Tesla. And the torque is given to us as 0.014 Newton meter. And initially the angle theta is 30. So we know torque is equal to mb sine theta. So m will be equal to torque upon b sine theta. So torque is 0.014 divided by b is 0.07 into sine of 30 degree. Solving this, we will get m equal to 0.4 ampere meter square. And secondly, we need to find out the work done in moving it from most stable to most unstable position. So we know for a magnetic field B, if you place a bar magnet, it will always try to align with the magnetic field. That is, its potential energy will be minimum along the magnetic field. Now if you try to move it opposite to magnetic field, that is by 180 degree, it will be at its most unstable position and its potential energy will be maximum. So we need to calculate work done for that. So W will be mb cos theta 1 minus cos theta 2. So we know m is equal to 0.4 into b is 0.07 into cos theta 1, that is where its potential energy is minimum for 0 degrees. So cos 0 minus cos theta 2, that is its most unstable position is at 180 degrees. So cos 180. So solving this, you will get W to be 0.056 joules. So this much amount of work is required to move the bar magnet in an external magnetic field from most stable to most unstable position. Let's look at the next sum. A magnetic needle is suspended freely so that it can rotate freely in the magnetic meridian. In order to keep it in the horizontal position, a weight of 0.2 gram is kept in one end of the needle. If the pole strength of this needle is 20 ampere meter, find the value of vertical component of the Earth's magnetic field. So solution. So there is a magnetic needle and there is a weight of 0.2 gram placed here in order to keep it in horizontal position. Now we know that Earth's magnetic field is not uniform. So suppose this is the Earth's magnetic field. So the Earth's magnetic field have two components, that is horizontal component and vertical component. So this will be the vertical component for this needle. Now the torque will be generated due to the vertical component, since the horizontal component will make 0 degree angle with this magnetic needle, so torque will be 0. So this torque will try to move this magnetic needle downwards, but since there is a weight, so this weight will try to act as a restoring torque. So this restoring torque will be equal to force into this length of the needle, that is L, and this restoring torque will be equal to the torque that will be due to this vertical component of magnetic field in order to keep this needle stable, which will be equal to MBV sine theta. Since theta is 90 degree, so this sine theta will be 1, so I can just remove the sine theta. From this we can say that BV, that is the vertical component of Earth's magnetic field, will be F into L upon M. F is the weight of the mass that is suspended from this needle. So BV will be equal to F, that is 0.2. Since this is 0.2 grams, so this will be 0.2 into 10 raised to minus 3 kg into 9.8, that is acceleration due to gravity, into L, that is the length of the needle divided by magnetic moment. Now magnetic moment is length of the pole, that is 2L into, this is the length of the pole, 2L, so this half is the L. Okay, and we are calculating torque for this half. So M will be 2L into pole strength, which is 2L into pole strength is given to us as 20 ampere meter. So let's put this value. So M will be 2L into 20. So 2, this will be 0.1, L will get cancelled, 2 will get, this will be 4.9 into 10. So calculating this, will get BV equal to 4.9 into 10 raised to minus 5 Tesla. I hope you understood this sum. Let's look at the last sum. The susceptibility of a paramagnetic material is chi at 27 degrees Celsius. At what temperature its susceptibility will be? Chi by 3. So solution, we know that susceptibility is inversely proportional to temperature. So the susceptibility at temperature 27 degree will be chi 1, and the susceptibility pi by 3, let's take it at chi 2, which will be T2 by T1, and here T1 is equal to 27 degree Celsius, which is 300 degree Kelvin. We need to calculate T2, which implies T2 will be equal to T1 into chi 1 upon chi 2. So since chi 1 is chi, that is at 27 degrees Celsius, T1 is 300 degree Kelvin into chi 1 is chi divided by chi 2, that is chi by 3. So this will get cancelled and 3 will go up, which will be 900 degree Kelvin. So at temperature 900 degree Kelvin, the susceptibility will be one third of the original susceptibility at 27 degree Celsius. So 900 degree Kelvin can be written as 627 degree Celsius. So this is the temperature. I hope you understood these sums that we did today. Thank you for watching.